A pleasant morning to all. Today, the presenters will have an in-depth discussion and review about the journal entitled Microstructure and Properties of Thermal Electrode. Materials silicon nitride molybdenum silicide composite ceramics as part of their course. Learning outcome. This presentation, aforementioned article. We hope.
Hello, my name is Romelin, one of the presenters for this group, and today I am going to discuss to you the background of the study, the theoretical background, the materials and equipment used in the study, and the procedures, the approaches used in this fact-finding work. And I hope you enjoy listening and learning to this one. In many industrial areas, the thermocouple is the most commonly used temperature testing device. In order to perform accurate temperature testing in a high temperature and corrosive environment, a corrosive and high temperature resistant tube must be used to secure the metallic thermocouple material. Yet, the use of a protection tube reduces thermocouple stability and accuracy due to changes in thermoelectrical potential caused by changes in the physical status of the metal electrode materials. Given the increasing demands from various fields of engineering, the stable features of thermocouple materials that can be used in high temperature and corrosive environments remain a major challenge in material science, particularly when they are used as the temperature testing device in molten salt electrolysis. In addition to the temperature range, the testing accuracy must be considered. Hence, when exposed to the aforementioned working environments, a traditional metal thermocouple couldn't satisfy the requirements. With this, ceramic-based composites which have good high temperature and corrosive resistance performance have been used as candidate materials to replace metallic thermocouple materials. Ceramic composite silicon nitride molybdenum silicide, according to prior research, has good mechanical, antioxidation, and corrosive resistance ability. It can therefore be used as a candidate material for metallic thermocouple materials. The mechanical and electrical features, as well as the microstructure of the composites, were investigated in the study in order to gain understanding on their potential uses as new high temperature and corrosive resistance thermocouple materials. According to Hebser, intermetallic compound molybdenum silicide has long been known as a high temperature material that has excellent oxidation resistance and electrical or thermal conductivity. Also, its low cost, high melting point, relatively low density, and ease of machining make it an attractive structural material. However, the use of molybdenum silicide has been hindered due to its poor toughness at low temperatures, poor creep resistance at high temperatures, and accelerated oxidation at temperatures between approximately 450 to 550 degrees Celsius. Addition of about 30 to 50 volume% of silicon nitride particulate to molybdenum silicide improved resistance to low temperature accelerated oxidation by forming a silicon oxynitride protective scale and thereby eliminating catastrophic pest failure. The silicon nitride addition also improved the high temperature creep strength by nearly 5 orders of magnitude, double the room temperature toughness. The composite exhibited excellent strength and toughness improvement up to 1400 degrees Celsius. This relatively supports why the research study exists. The main concept of this fact-finding work is to utilize ceramic composite silicon nitride molybdenum silicide to find an alternative raw material in the process of making thermocouple electrode materials that, unlike metallic materials, can withstand demanding environments such as high temperature and corrosive settings and possesses lesser adverse effects. The availability of the selected ceramic composite samples in the locality is very essential to make use of the potential replacement of metallic materials. This indicates the framework of this investigation, wherein the discovery of potential alternative raw material for thermocouple provides a feasible solution of the main concept of the research problem. The Followings are the materials and equipment used in the study. We have silicon nitride powder, molybdenum silicide powder, ethyl alcohol, argon gas, graphite mold, hot press machine, ball mill, vacuum furnace, universal testing machine used for three-point bending method, Rigaco D Max RAI X-ray diffractometer for XRD, Hitachi S4700 scanning electron microscope for SEM or EDS, and ZIS MC80DX for optical microscopy. Now we will discuss the procedures for this fact-finding work. First is the collection of samples. The silicon nitride powder sample was collected from Shinure Company in Fuzhou, China, while the molybdenum silicide powder sample was obtained from Yantai Torch Special High Temperature Ceramics Company in Yantai, China. Without further purifications, all materials were used and received. Next is the identification of the chemical contents and microstructure of the samples. So the chemical contents and microstructures of the powders were determined as shown in Table 1 and Figure 1 respectively. Based on the data shown, the purity of the silicon nitride was higher than 92% with an average size of 1 micrometer. Furthermore, the purity of lanthanum oxide and molybdenum silicide was higher than 99% with size of 10 micrometer, and the purity of yttrium oxide was higher than 99% with an average size of 15 micrometer. Next is determining the constituents of the samples. The constituents of the samples were listed as shown in Table 2. Sample number 1 has 68% of silicon nitride, 38% of molybdenum silicide, and 5% each for lanthanum oxide and yttrium oxide. To add, sample number 2 is composed of 5, and 5% of silicon nitride, molybdenum silicide, lanthanum oxide, and yttrium oxide respectively. Finally, sample number 3 is constituted of 38% of silicon nitride, 68% of molybdenum silicide, and 5% each for lanthanum oxide and yttrium oxide. Now for hot pressing method, the powders were first ball milled in dehydrated ethyl alcohol for 10 hours before being dried in a vacuum furnace at 100 degrees Celsius. After drying, the temperature was raised to 1750 degrees Celsius at a rate of 30 degrees Celsius per minute, followed by a 25 MPa hot pressing and a 60-minute soak in a graphite mold. Note that from the start of the hot pressing procedure, the furnace chamber was cleared out with 0.5 atm of argon gas. The relative densities of the prepared samples were then tested according to the Archimedes method. Next is flexural strength test and thermal shock resistance test. The flexural strengths were tested through a three-point bending method in a universal testing machine. The size of the samples were 3 by 4 by 36 cubic millimeter, and the flexural strength were calculated according to the following equation, where F is the fracture loading, L is the space between the 2 points, and B and H are the width and thickness of the samples respectively. The loading rate was 0.5 millimeter per minute. Note that before testing, the surfaces of the samples were polished to avoid stress concentration. On the other hand, thermal shock resistance is one of the most important properties of ceramic materials. It reflects the fracture resistance of a material with exposure to sharp temperature change conditions. In general, the thermal shock resistance can be characterized by the strength remaining rate after thermal shock testing, expressed by the second equation, where Nrem is the flexural strength remaining rate, sigma T is the flexural strength of the material experienced and time thermal shocking at temperature T, and sigma 0 is the original flexural strength. The samples for the remaining strength tests were air-cooled at various temperatures 10 times. The final results for both tests were the arithmetic average value of 3 samples. Finally, the phase structures were determined by X-ray diffraction pattern on a Rigaco D Max RA X-ray diffractometer with copper K alpha radiation. The surface morphologies of the samples were observed by the scanning electron microscopy with energy dispersive spectroscopy, performed on a Hitachi S4700 scanning electron microscope. After that, the cross-sectional optical microscopy was observed on ZIS MC80DX.
Good day everyone, I am Rona AGBAY-CALUNSAG, one of the reporters today, and I'm going to present to you the discussion of results and also the conclusion.
Results and discussion of results. First, we have the XRD results and optical microstructure. The figure on the left shows the XRD pattern of the silicon nitride molybdenum disilicide composites. The composites, after hot compressing, were mainly composed of the beta silicon nitride and molybdenum disilicide phase. Neither yttrium nor lanthanum compounds were detected. Based on this result, it can be claimed that during the hot pressing process, the original alpha silicon nitride changed to beta silicon nitride. The sintering additives, yttrium oxide and lanthanum oxide, reacted with the silicon and oxygen content and form an amorphous glassy phase. In addition, small amounts of molybdenum silicide phase can also be detected. The figure on the right shows the densities of the prepared samples. The densities of silicon nitride with 30 weight percentage molybdenum disilicide, silicon nitride with 45 weight percentage of molybdenum disilicide, and silicon nitride with 60 weight percentage of molybdenum disilicide were 4.66 grams per cubic centimeter, 4.31 grams per cubic centimeter, and 3.99 grams per cubic centimeter respectively. After calculation, the relative densities of the samples were 93.5%, 94.9%, and 95.7%. Samples were all well sintered with a relatively low porosity of less than 6.5% as seen in the results. It was found that with the addition of the yttrium and lanthanum, the densification could be significantly improved. Figures 4 and 5 show the optical microscopy, backscattering scanning electron microscope, and transmission electron microscopy images of silicon nitride with 30 weight percentage molybdenum disilicide, silicon nitride with 45 weight percentage of molybdenum disilicide, and silicon nitride with 60 weight percentage of molybdenum disilicide respectively. In the optical microscope and backscattering electron microscope, the white areas are the molybdenum disilicide phase and the dark areas are the silicon nitride phase. As seen in the figures, these two phases were evenly distributed, and the interfaces between the two components were clear and smooth. Little micro cracks could be observed. The size of the silicon nitride was about 3 to 8 micrometer, and the size of the molybdenum disilicide was about 3 to 5 micrometer with a uniexial shape. In addition, the size of the silicon nitride slightly reduced with the increasing weight contents of molybdenum disilicide. Figure 6 shows the flexural strengths of the silicon nitride molybdenum disilicide composites. The flexural strength of the composite reached 942 megapascals, which was higher than that of the pure silicon nitride, which was 781 megapascals. When the filling content of molybdenum disilicide reached 30 weight percentage. However, the flexural strength started to decrease with increasing molybdenum disilicide content over 30 weight percentage. The flexural strength decreases to 535 megapascals when the molybdenum disilicide reached 60 weight percentage. Figure 7 shows the scanning electron microscopy morphology of the silicon nitride molybdenum disilicide composites. As demonstrated in this figure, the fracture of the composites was a typical intergranular fracture. The grains of the silicon nitride were rod-shaped and the grains of the molybdenum disilicide were equiaxial. In sample number 1, the grain size of the molybdenum disilicide was relatively small with a size of about 3 to 5 micrometer. An increase of molybdenum disilicide content makes the grain size of the molybdenum disilicide kept increasing slightly, and small amounts of randomly distributed rod-shaped silicon nitride crystals were observed among the molybdenum disilicide crystals. It can be concluded that the addition of the molybdenum disilicide, the flexural strength of the composites will start to decrease when the content of the molybdenum disilicide is higher than the critical value due to the increase of porosity and residual stresses. Figure 8 presents the flexural strength remaining rate of the silicon nitride molybdenum disilicide composites at temperatures of 500 degrees Celsius, 600 degrees Celsius, and 700 degrees Celsius after thermal shock testing 10 times. As demonstrated in this figure, the flexural strength remaining rates were 85.2%, 60.5%, and 23.4% corresponding to samples 1, 2, and 3 respectively, when the thermal shock temperature was 500 degrees Celsius. When the thermal shock testing temperature increased to 600 degrees Celsius and 700 degrees Celsius, the flexural strength remaining rate was lower than 20%. Figure 9 shows the scanning electron microscopy microstructure of the fracture surface of sample number 1. As demonstrated in this figure, microcracks could be clearly observed when compared with the samples without thermal shock experience. In addition, the quantity and size of the microcracks increased with increasing thermal shock testing temperatures, which resulted from the internal stresses due to the thermal expansion mismatch. As a result, the flexural strength decreased with an increasing internal stress and thermal mismatch of the two main constituents. Electrical conductivity. Figure 10 illustrates the electrical conductivity of the silicon nitride molybdenum disilicide composites as a function of the filling content of molybdenum disilicide. As shown in this figure, the addition of molybdenum disilicide could considerably increase the electrical conductivity of the composites. When the content of the molybdenum disilicide reached 30 weight percentage, the electrical conductivity was 1.25 times 10 to the negative 5 per ohmmeter. When the content increased to 45 weight percentage, the electrical conductivity increased 7 orders of magnitude and reached 3.45 times 10 squared per ohmmeter. After this value, the electrical conductivity increasing rate becomes flat. This phenomenon can be explained by the percolation theory. Before the percolation threshold, which means that the content of molybdenum disilicide is relatively low, the molybdenum disilicide is randomly distributed in the matrix, but no percolation network can be formed. Under this condition, the electrical conductivity is mainly determined by the matrix material and shows low electrical conductivity. When the molybdenum disilicide content increased above the percolation threshold, the percolation network of molybdenum disilicide formed, and as a result, the electrical conductivity was mainly distributed by the molybdenum disilicide phase rather than the matrix, thus showing high electrical conductivity. In this study, it can be claimed that the percolation threshold is located between 30 weight percentage to 45 weight percentage. Conclusion. In summary, this study successfully prepared silicon nitride molybdenum disilicide composites with hot pressing technology. The main constituents of the hot press silicon nitride molybdenum disilicide composites were beta silicon nitride and molybdenum disilicide, and also a small amount of molybdenum silicide phase and glassy phase containing lanthanum and yttrium. The SEM morphology of the silicon nitride molybdenum disilicide composites demonstrated that the fracture of the composites was a typical intergranular fracture. The grains of the silicon nitride were rod-shaped, and the grains of the molybdenum disilicide were equiaxial. The strength of the silicon nitride molybdenum disilicide composites decreased with increasing molybdenum disilicide content. The flexural strength remaining rate of the silicon nitride molybdenum disilicide composites at temperatures of 500 degrees Celsius, 600 degrees Celsius, and 700 degrees Celsius after thermal shocking testing 10 times demonstrated that the flexural strength rates were 85.2%, 60.5%, and 23.4%, corresponding to the silicon nitride with 30 weight percentage of molybdenum disilicide, silicon nitride with 45 weight percentage of molybdenum disilicide, and silicon nitride with 60 weight percentage of molybdenum disilicide respectively, when the thermal shock temperature was 500 degrees Celsius. When the thermal shock testing temperature increased to 600 degrees Celsius and 700 degrees Celsius, the flexural strength remaining rates were lower than 20%.
Okay, to support the theoretical background of the methodology, obtaining raw materials without doing further purification enables us to clearly compare improvements or deteriorations in the composites. Purity levels are having high rates greater than 92%. Constituent samples of different compositions have variations in their strength and intensities of characteristics. To support the theoretical background to the results and discussion, a positive feedback was obtained upon forming composite that the temperature range is still being considered, and also with respect to the different formulations tested. Silicon nitride molybdenum disilicide resulted in a good mechanical, antioxidation, and corrosive resistance performances and is positive in the potential application as new high temperature and corrosive resistance thermocouple materials. The density of the samples were 93.5%, 94.9%, and 95.7%, which are relatively high. The samples are all well-centered with a relatively low porosity of less than 6.5%. The two phases were evenly distributed and their interfaces were clear and smooth, though microcracks are still observed. The silicon nitride molybdenum disilicide have high flexural strength compared to the pure silicon nitride. Flexural strength at 500 degrees Celsius during thermal shock testing, which is done 10 times, has rates of 85.2%, 60.5%, and 23.4%, corresponding to the samples 1, 2, and 3. The samples has a remaining rate less than 20% when the temperature is increased to 600 degrees Celsius and 700 degrees Celsius. Molybdenum disilicide addition will considerably increase the electrical conductivity of the composites. For the recommendations of improvements, if able, one of the recommendations analyzed here is that the number of samples to be tested will be better if it is a larger set of different variations to know the limits of each composite samples. Also, trying other composite materials as one of the raw substance to know other alternatives and forming another set of unique properties of a composite material. Powders, lanthanum oxide, and yttrium oxide are not introduced properly in the study. It requires a little background in this area and the effects it will contribute in the composite. So, to criticize the results and corresponding discussion of the results, the addition of the yttrium and lanthanum was found out to significantly improve the densification. So maybe a little variation of the next formulation will have an improvement in the outcome. So, is citation properly deserved? Yes, in the study, references and citations are done in the right way and placed accordingly. So, that's all. Thank you.
And now let's go over to my review for this one. Support of the theoretical background to the methodology. Influenced by the aforementioned supporting literature, the researchers also conducted various tests involving the ceramic-based composites microstructure, mechanical, as well as electrical properties, which greatly contribute to the composite's potential as a candidate material for metallic thermocouple materials. Determining the tests to conduct and the methods is very vital in this research work, as well as other works, as it paved a way for an in-depth analysis if this study really provides a feasible solution to the main concept of the research problem. Support of the theoretical background to the results and discussion. After various tests, the ceramic-based composites exhibited significant results concerning their microstructure, mechanical, and electrical properties that greatly affect the composite's promising uses as one of the raw materials for the commonly used temperature testing device in numerous fields of engineering as expected due to the provided related literature. As what is aforementioned in the results part, samples like sample number 1 and 2 shows relatively high flexural strength even greater than that of pure silicon nitride. On the other hand, the sample's flexural strength remaining rate after being subjected to 10 thermal shock tests at 500 degrees Celsius thermal shock temperature were relatively high too. Moreover, samples with high molybdenum silicide content exhibited high electrical conductivity as well. Identifying any assumptions on XRD results in optical microstructure, they claimed that during the hot pressing process, the original alpha silicon nitride changed to beta silicon nitride. The sintering additives yttrium oxide and lanthanum oxide reacted with the silicon and oxygen content and formed an amorphous glassy phase. On flexural strength, they concluded that with the addition of molybdenum silicide, the flexural strength of the composites will start to decrease when the content of the molybdenum silicide is higher than a critical value due to the increase of porosity and residual stresses. On electrical conductivity, they claim that the percolation threshold is located between 30 weight% to 45 weight%. Identifying any ludicrousness in the methodology results in discussion. As what I have observed, there were no absurdity or exaggeration along the research work. Recommendations on the methodology. So I highly recommend the researchers to elaborate the reason why they included the powders lanthanum oxide and yttrium oxide, as they did not introduce this in the first place. Giving us an elaboration about this first would definitely help us not to get confused as we process and comprehend this study. In the hot press method, the researchers must have explained the use of argon gas for clearing out the furnace chamber and the use of Archimedes method in calculating the relative densities. It may be right to provide a little introduction about these things to avoid confusion to the newbies such as myself. Finally, it would also be nice if they could just be detailed and organized with their step-by-step process in order for the study to be easy to replicate or conduct and enhance for future experiments. My comment for the results and corresponding discussion of results. In the results section, obviously, the resulting values of the samples of ceramic-based composites for each test were highlighted. However, it may be relevant to include in the statement the ceramic composites' potential application as new high-temperature and corrosive resistance thermocouple materials, like comparing these results to those of the traditionally used metallic thermocouple. To simply put, the researchers must have addressed what they have discussed in the introduction part that led to the execution of this fact-finding work. And is citation properly observed? As what I have noticed, yes, the citations are properly observed, and establishing this greatly helps in tracing the related and supporting literatures for this study.
Thank you for listening. Got any questions? You can raise that after this